You're standing at a window. Rain streaks down the glass. You're looking through it, not at it. Because that's what glass does best. It erases itself. Here's what nobody mentions. The material in that window is chemically almost identical to the sand on a beach. Silicon dioxide, SiO2. Take a handful of ordinary sand, melt it above 1,700 degrees Celsius, cool it fast enough, and one of the most common minerals on Earth becomes one of the most useful materials humans have ever made. The beach scatters light, the window doesn't. Same molecule, radically different behavior. The real question isn't why glass is transparent. Materials scientist Mark Miodownik framed it sharper than that. Why isn't everything transparent? Atoms are mostly empty space. Light should pass through anything. The fact that most of the world is opaque requires an explanation. That explanation involves electron seats, forbidden energy levels, and a gap so precise it lets an entire color spectrum pass through undetected. The answer changes more than you'd expect. Welcome to Object Lore, where history hides inside the things you use every day without a second glance. Today's object is in every window, every microscope lens, every phone screen, every greenhouse panel, and every pair of glasses you've ever worn. You probably assume glass is a liquid, a very slow-moving one. The reasoning sounds reasonable. Look at windows in old European cathedrals. The glass is visibly thicker at the bottom. The glass must have flowed downward over centuries, like cold honey. Some science textbooks have repeated this. It is not correct. Glass isn't a slow liquid. It is an amorphous solid, a material whose atoms are locked rigidly in place, but in a disordered arrangement rather than a neat crystal. Morton Tavel, professor of physics at Vassar College, describes it in Scientific American as mechanically rigid like a solid, yet with the molecular disorder of a liquid. Cathedral windows are thicker at the bottom because medieval glassmakers couldn't produce uniform sheets. Craftsmen installed the thicker edge at the base for stability. The glass hasn't moved in 600 years. And what glass actually is precisely what makes transparency make sense. Picture Murano, a small island just north of Venice, sometime in the 13th century. The Republic of Venice has ordered its glassblowers relocated there, away from the mainland city. The official reason, fire risk. The actual reason, control. Venetian glassmaking had become so economically valuable that its techniques were treated as state secrets. Murano's artisans were granted unusual privileges: the right to carry swords, permission for their daughters to marry Venetian nobility. In exchange, accounts suggest they were forbidden to leave. Those who attempted to take their knowledge elsewhere were, according to historical records, pursued. Some did not return. Glassmaking itself predates Venice by millennia. Archaeological evidence places glass objects in Mesopotamia and Egypt as far back as 3500 BCE, initially as glazes on pottery, then as molded vessels. Roman artisans produced flat window glass as early as the 1st century CE, recovered from excavations at Pompeii, but it was thin, greenish, barely translucent. The technical leap came with the crown glass method, used across medieval Europe. A blown bubble of molten glass was spun rapidly on an iron rod, flattening by centrifugal force into a large flat disc. Cut into panes, it produced the clearest glass available, uneven with a bullseye at the center, but clear enough to change architecture, clear enough, it turned out, to change science. The finest crown glass found its way into the workshops of instrument makers in the 16th and 17th centuries, exactly the people who were about to rebuild humanity's understanding of the universe. And then everything changed. Here's what most people assume about a glass window: building material, weather barrier, architectural convenience. That assumption misses 4 centuries of scientific consequence. In 1610, Galileo Galilei pointed a ground glass lens at the sky and observed 4 moons orbiting Jupiter, the first direct evidence that not everything in the cosmos revolves around Earth. In the 1670s, Antonia van Leeuwenhoek ground lenses so precisely they revealed bacteria and protozoa, for the first time in human history. An invisible world, opened by a curved piece of transparent material. Both discoveries depended entirely on one property: light passing through glass without scattering. Meanwhile, the British government had recognized glass's value in a more blunt way. In 1696, Parliament introduced the window tax. a property levy based on the number of windows in a building. More glass meant a higher tax. Wealthy homeowners responded by bricking up windows to reduce their bill. You can still see filled-in window outlines in Georgian-era buildings across the UK today. Architects began designing facades with false window recesses to maintain visual symmetry over what was now a wall. Transparency, in 17th century England, had become a taxable luxury. The greenhouse followed, not as metaphor, but literally. Glass enclosures built during the 18th century allowed tropical plants to be cultivated at northern latitudes, reshaping botany, agriculture, and colonial trade networks. But why light moves through glass at all, the actual physics, remained entirely unexplained for another 2 centuries. This is where it gets strange. Imagine an atom the size of a sports stadium. The nucleus sits at the center, a single P. The electrons occupy the far outer seats, near the top of the bleachers. Everything between them is empty space. This is the analogy materials scientist Mark Miodownik uses to frame the paradox. Atoms are overwhelmingly hollow. Light should pass through everything. The question is, what stops it? The answer lies in the seats themselves. Electrons don't occupy random positions. They occupy specific energy levels, fixed rows in that stadium. For an electron to move to a higher row, it needs exactly the right amount of energy. If a photon's energy matches the gap between rows, the electron absorbs it. The photon disappears. The material is opaque. In glass, silicon dioxide, the energy gap between electron levels is large. Photons of visible light, which range from 400 to 700 nanometers in wavelength, simply don't carry enough energy to bridge it. They pass through. Professor Phil Moriarty of the University of Nottingham, in the 60 Symbols Physics series, calls this the band gap, the single variable that separates transparent materials from everything else. Worth noting, you cannot get a suntan through a glass window. Ultraviolet light carries more energy than visible light and is absorbed by glass electrons. The pane is perfectly transparent to you, and a complete wall to the wavelength, actively trying to burn you. The glass sees you fine. You just don't see it working. Metals are the opposite, by design of their atomic structure. Morton Tavel of Vassar College explained it precisely. Metals are filled with free electrons, not bound to any particular atom. When light hits metal, these electrons absorb and immediately re-emit photons in the reverse direction. Reflection. No band gap, no transparency, just shine. Sand and glass share the same chemical formula. Structure alone determines everything. Today, the physics that makes a window transparent has been engineered into materials that have no right to be see-through. Aluminium oxynitride, ALON, is a transparent ceramic harder than standard glass, used in military transparent armor for aircraft and vehicle windows. It stops bullets, and you can see through it. Sapphire glass, crystalline aluminium oxide, covers the lenses of high-end watches and barcode scanners because it is virtually scratch-proof. The Eden project in Cornwall doesn't use glass panels at all. Its enclosures are built from ETFE, ethylene tetrafluoroethylene, inflatable pneumatic cushions. The material is more transparent than glass, significantly lighter, and more durable in polluted environments. The world's largest enclosed garden runs on a transparent plastic most people have never encountered. And the screen you may be watching this on right now contains indium tin oxide, a transparent conductive film that carries electrical charge while letting light through. Every smartphone touchscreen, every solar panel electrode. Transparency, conducting electricity. The property that makes a window work has quietly migrated into almost every piece of technology you own. The tone is about to shift, so the next time you look through a window, consider what you're actually doing. You're passing light through a disordered solid engineered, at the molecular level, to fail to interact with it. That same failure let Galileo see Jupiter's moons. Let Van Leeuwenhoek see bacteria. Let architects build greenhouses and engineers build solar panels. The most useful thing about glass is that it isn't there. And yet, quietly, invisibly, across 4,000 years of human history, It has been the lens through which the modern world was built. If this changed how you see the glass around you, tell us what you think should be next. Drop a comment below. What material, what object, what everyday thing do you think has a hidden story most people have never heard? We'd love to know. This is Object Lore. The history of the world is hiding in plain sight. Until next time.